Welcome everyone to this lecture this evening on climate science. So my name's Matt Collins. I'm a professor here in mathematics and also something which sounds rather grand, the joint Met Office chair in climate change. It just means I have a strong working relationship with the Met Office in terms of the research that we do here on climate change, and there are many such interactions. We appreciate that also you may be missing such delights as the final of the Great British Bake Off, so I won't reveal who the winner is. So it's our great pleasure to welcome Stephen Belcher, who is the chief scientist of the Met Office, which kind of puts him as being, you know, perhaps the most senior meteorologist and weather and climate scientist in the UK. Stephen has had already an august career. He did a PhD in Cambridge, supervised by Lord Julian Hunt, who was also in fact, he was a previous Director General of the Met Office. So that goes back a bit if it was a Director General. Sounds like an old term. Stephen was then a postdoc in Stanford University, and then back at Cambridge, have I got that in the right order? And then he was a lecturer in Reading, head of Department of Meteorology in Reading, and head of school in Reading as well. And most recently, he's been the Director of Climate Research at the Met Office, the Director of the Hadley Centre, and last year was promoted to the position of Chief Scientist. So I will, without further ado, hand over to Stephen, who will speak. We'll have some time for questions at the end. We're live streaming this, apparently, so it means that when we ask questions, we'll need to use microphones. So there'll be, if you could ask a question, please sort of hold on to it and wait before we give you the microphone. But otherwise, over to Stephen.
There they are. Okay, well, good evening, everybody, and thank you for the opportunity to give this presentation to Matt and the members of the university. I'm delighted to be here as the Met Office Chief Scientist. With the Met Office so close to Exeter and the university, we have a very special relationship with the city and the university, which is perhaps encapsulated in part by this lecture. I should say I'm just getting over a cold, so I'm not quite my usual animated self, and if I sound a little bit slow, that's the reason. Okay, so what I would like to discuss this evening is the needs and requirements of climate science following the Paris Agreement. So I'll come back to this later, but many of you will be aware that in almost exactly 2 years ago, there was a meeting called the Conference of the Parties in Paris, which made some very significant progress towards addressing climate change. And really this agreement, I think, has changed the agenda for what scientists who study the climate need to be doing now. So that's the subject of my lecture. And I should say, anticipating potential questions, that I am not a political scientist, I am a physical scientist. So you can ask questions about the politics side, but I will dive back into the physical science. Okay, so 2015, I think, if you have an interest in the Earth's environment, should be one of those years when you ask yourself, what was I doing in December 2015? Because there were three very significant events in this year. One was this meeting in Paris, which I mentioned earlier. So this is the Conference of the Parties. So there's a meeting of this group every year of our political leaders who have negotiations about the amount of carbon dioxide each of our countries emits into the atmosphere and potential measures for reducing that emission of carbon dioxide. And the significance of the Paris meeting in 2015 was that agreement was made on how to limit those. And again, I'll come back to that on my next slide. If that wasn't enough, and this was a very, very substantial step forward in international negotiations, 197 countries signed up to this deal. So can you imagine 197 politicians all agreed to one thing? Took a while to get that one sorted out, I'm sure. In addition to that, the United Nations has a responsibility to think about how the world protects itself from weather disasters. And so it launched the Conference on Disaster Risk Reduction, also now known as the Sendai Conference. So particularly in developing nations in the world, when a hurricane hits or a drought hits, the consequences are really very profound for that country, and the UN has launched this disaster risk reduction initiative to try and pool international funding and international expertise to help particularly developing countries in that sphere. And the third element of 2015 was that the United Nations also launched its new Sustainable Development Goals. So this is a list of 17, yes, 17. It's a prime number, but other than that, I don't understand why it's 17. 17 goals to be addressed over the next 20 to 30 years to try and make the world a better place. And these goals revolve around poverty, hunger, health and well-being, a whole raft of things. What else do we have? Cities and communities, climate action is an explicit one here, something on the oceans, peace and justice, etc. And what, as a weather and climate scientist, what's very striking to me about this list of goals is that weather and climate sits under many, many, almost all of these goals, in fact. Poverty requires, the food one I was going to talk about. So zero hunger, we need productive agriculture that can feed a growing population. Well, agriculture is highly dependent on weather and climate. The oceans are part of the climate system. We know that greenhouse gases are being absorbed by the oceans, and carbon dioxide makes them more acidic, which has implications for life in the oceans. So actually you can go through many of these sustainable development goals and see a contribution to weather and climate. So as I say, when taken together, 2015 really set the stage for weather and climate community to think about how we can contribute to these important sort of world goals. Just to add a little bit more detail on the Paris Agreement, here's an infographic that we made sort of trying to summarize what was discussed and agreed upon at Paris. So firstly, this line here, and you'll see this again in a later slide, is the global mean temperature from 1850 through to present day. So we take observations of temperatures around the globes, the oceans, in the atmosphere, and we average those to make one temperature, an average temperature which characterizes the temperature of the Earth, and put those together to make this long time series, and you can see the warming of about 1 degree above pre-industrial levels present day. So two of the goals of the Paris Agreement was firstly to limit warming below 2 degrees, and if possible, follow aggressive measures or an aspiration to limit global average temperature rise to 1.5 degrees. Well, given that global temperature has also already increased by 1 degree, you can see what an aggressive and ambitious target this is. And so as scientists, the question that we need to address is, can that be achieved within physical bounds of the climate system? The way the Paris Agreement wants to address this challenge of keeping global temperature below these limits is firstly a long-term aim to reach zero net emissions of carbon dioxide by 2050. So as we emit more carbon dioxide and other greenhouse gases into the atmosphere, the temperature rises. It's the accumulated concentrations of these gases that causes the warming. So in order for the temperature to stabilize, we need to stop emitting any further carbon dioxide into the atmosphere. So hence this ambition here. Now at the moment, this schematic shows something like the trajectory of our emissions we'll have to follow if we're going to achieve that. At the moment, our emissions of carbon dioxide are still increasing. They're somewhat level actually at the moment, but they will need to peak and then reduce down to zero. And so there's a huge amount of work trying to understand when we would need to peak in order to have any chance of reaching zero and then staying below this 1.5 or 2 degree target. There are several process elements to this. So 197 countries with very different sets of ethics and governance systems. So how would we understand whether each of these countries is honouring its commitments. And so there's a bunch of more governance elements to the Paris Agreement, such as global stocktakes. So as scientists, how can we assess or how can we make measurements that tell us whether or not the UK really has emitted what it said it would emit, or has it emitted more than that? There needs to be a monitoring side of this. It's recognised that the current volume or weight of carbon dioxide in the atmosphere, a large fraction of that over history has been contributed by the developed world. In fact, if you look at historically integrated emissions, total carbon dioxide emitted to the atmosphere since the Industrial Revolution, the UK sits at number 2. So we may be rather low emitters now, but when we look at our debt or our legacy of carbon dioxide, we're second only to the United States. So we participate in the Green Climate Fund to help support the developing nations to evolve into a climate-sensitive economy. There's a very controversial subject of loss and damage. So supposing the climate warmed sufficiently that some states were damaged in a very profound way, so some of the low-lying states in the Pacific, if sea level were to rise and decimate their current territories, should the perpetrators of this pay for it in some way? So this comes under the heading of loss and damage. I say it's very controversial because how would we attribute blame? You know, this is a whole legal jungle which I have no qualification to talk about, so I will leave it there. And then finally, something which I think is very close to the Met Office's ambitions now is to build resilience and reduce vulnerability to the unavoidable impacts of climate change. So since the Industrial Revolution, greenhouse gas concentrations have increased. We're now exceeded 400 parts per million in carbon dioxide. So the climate has changed and will continue to change for the next several decades. And so building resilience to those changes is something really important. And actually, the UK government has responded in a very positive way. There's much more funding over its overseas development assistance programme to address just these challenges in the developing world. And Exeter as university has made some fantastic contributions to that agenda. So that's kind of scene setting, I suppose, for what, as a climate scientist, what do we need to do over the next 5, 10 or 15 years? And we have been thinking about this as a community, and so the climate scientists in the audience, I think, will not see surprises here, at least I hope they won't. And I tend to think of them something around 5 questions. So the first is, we need to clearly have a pulse on planet Earth and understand what the climate system is doing now. We've got this very aggressive target of keeping global mean temperatures between below 1.5 and possibly 2 degrees, possibly 1.5. If we're at 1 now, we need to understand where we are in real time to sort of chart our approach to those targets. Can we achieve the Paris target? So this is really about emissions. What emissions of carbon dioxide will still give us a chance of keeping us below these warming targets? On the resilience side, what are the present and future extreme weather and climate hazards? So this is thinking about building the resilience and reducing the vulnerability to climate. So thinking about weather systems, how will the weather, the character of the weather change as our climate changes? What are the risks and impacts of mitigation adaptation actions? So this really is about how the weather could be in a future climate. This is about what would the implications of that potential change of weather or sea level be on flooding or agriculture and other kind of human and natural systems. And one here on the technical side, which I may get to, is the climate science and weather science is a very big science. You need enormous computers to be able to do the work that we do. And there's a technical challenge out there that our computers are changing very fundamentally in their architecture. So there's kind of one for the technologists there as well. So in the remainder of my time, I'm going to step through each of these 5 questions and just give you a flavour of what we might do that sits under those, and then I'll try and draw some threads together at the end. Okay, so what's happening now? Well, I've already kind of given you a taster of this. This is the global mean temperature. So there are 3 main centres in the world that maintain a global mean temperature record. So the Met Office is one of them, working with the University of East Anglia Climate Research Unit. NOAA in the United States and NASA GIS, also in the United States. I think you had, the name's gone, speaking to you recently. Gavin Schmidt, thank you, Tyrone, who's the director of the NASA GIS Institute. And so this is showing you the temperature from those records, 1850 up to present day. And in fact, here we've got the most recent figures from the Hadley Centre. So the different coloured lines here represent those different data sets. So the black line is Met Office, the orange line is NOAA, and the blue line is NASA. So you can see they're broadly similar. There are some differences in detail, but the overall picture they tell is the same, namely of a strong warming signal, particularly towards the end of the 20th century here. Now, this is temperature on the vertical axis, and what climate folk always do is to plot this as a difference of temperature. So how much has the global mean temperature warmed since some predefined baseline? So given that the targets at Paris were set against a pre-industrial climate, so limit warming below 2 degrees and if possible 1.5, there's an implication of pre-industrial temperatures, and so that's what this has been baselined. And just as an aside, there's quite a big debate at the moment in the climate science community of what represents a pre-industrial baseline. And I don't know if there are any historians in the audience, but some of you may have noticed that 1850 to 1900, the Industrial Revolution was going pretty strong by that stage. So why are we using that as our pre-industrial baseline? It's a simple, expedient and practical thing that our observations only reliably go back to that period. But there is this big debate about how could we get a more reliable pre-industrial level. Anyway, that aside, if we take that as our baseline, we see a warming in the early 20th century, a levelling off, and the likelihood is that this levelling off is partly natural changes in the climate system. The global mean temperature does vary year to year. But also, this was a period post-Second World War of enormous industrialization. And as part of that industrialization, there were huge emissions of small particles, which climate scientists rather perversely called aerosols. These are not the things you spray under your armpits, but these small particles of soot and other chemical species that form in very small particles in the atmosphere that reflect sunlight. So sunlight comes from the sun, and these act like little mirrors in the atmosphere and reflect back the sunlight. And so part of that cooling, a lack of warming in that period, is probably due to higher concentrations of these aerosols in the atmosphere during the post-war industrialization. We can then see the rapid warming in the 70s and 80s, the end of the last century, and a much discussed slowdown or pause or hiatus in the warming in the early parts of the 20th century. So there was a website which was showing this curve, but only from about 1998 onwards, which is that year, saying there's been no warming this century. Well, it's been a heavily discussed scientific topic, and clearly when taken in this context, that doesn't make sense. But also the last 3 years, we've seen record-breaking temperatures. This year probably won't be a record. It'll be the 2nd or 3rd warmest year on record. But you can see it's well above the pack. So we've got those years there. Okay, so this concept of kind of keeping what's happening to the Earth real time is an important part of the mission. And to give you previous plot maybe helps us understand how we're doing compared to this 1.5 degree target. This is a second kind of example, which is the Arctic sea ice. So this is looking down on the North Pole here. So let's see, there's the UK, Scandinavia, northern Russia, Canada, Alaska, and northern Canada here, Greenland. This map is showing the sea ice extent roughly when we get minimum. There's The sea ice tends to shrink during the summer for obvious reasons. The oceans warm up during the summer, and then it expands during the winter as you get the colder ocean temperatures. This map shows from satellite imagery the minimum extent of the sea ice, and this orange is showing more of an average for an earlier period. So this was quite a low level for the sea ice. Why would we want to know that? Well, partly to understand what the climate's doing. The Arctic is one of those iconic aspects of the climate. We know the poles are warming more than the middle and latitudes in the tropics. But also there are practical implications of this. So there are nations interested in mining the ocean floor around these regions, or introducing shipping routes around the Arctic Ocean. So an element of this monitoring what's happening to the climate system is there to provide that kind of information. As the climate's changing, how might we want to use the climate, or exploit, that's the wrong word, work with the climate system. Yeah, I think I'll leave that. Okay. So the Paris targets, they're very aggressive. We've seen warming of just over a degree above pre-industrial now. The main tool that we have for assessing this progress is this figure, and I'll take a few minutes to explain it because it is a little involved, but I think once the penny drops, it's a very helpful sort of one-stop shop. What's shown on this horizontal axis here is the total amount of carbon dioxide, or greenhouse gas equivalent, that's been emitted in the into the atmosphere since 1870. So we add up this carbon dioxide emitted in 1870, 1871, 1872, and so on. For every year, we just keep adding up how much carbon dioxide has been added, and we get this cumulative total. So this is the total amount of carbon dioxide that human activities have put into the atmosphere. And this axis here is the temperature, the amount of warming we would expect to get by increasing the carbon dioxide loading in the atmosphere. So it turns out, and it's not obvious when this was begun, that there's a roughly straight line relationship. So as we keep adding carbon dioxide to the atmosphere, so the temperature warms. So if we want to stabilize the temperature at, say, 2 degrees, once we've emitted that much carbon dioxide into the atmosphere, through the course of our history, we will need then to not emit any more carbon dioxide net into the atmosphere. So let me just recap on that. So what this tells us is if we have a warming target of 2 degrees, we can read off how much carbon we can emit into the atmosphere. So it gives us a budget. And to give you some context, through the course of history since the Industrial Revolution, this is roughly where we are in the amount, so 555 of gigatons of carbon equivalent. I don't know what a gigaton is, but it's a lot. I don't have a way of visualizing that. And you can see that corresponds, as we observe, to a temperature of roughly 1 degree. In order to get 2 degrees, that gives us about 55, an additional 55 gigatons. I've got my numbers wrong here. Tyrone, help me. So in order to achieve 2 degrees, you could see we're at about 750, something like that. So we're about 2/3 the way there already. So that's the scale of the challenge. Our emissions are rising. They haven't risen so much in the last few years. So we've got a major challenge to address here. That's point number one. Point number two is that this emphasizes that climate science is now really about numbers. So when I started working in this field 20 years ago, the question was really, is the climate changing? And if it is it due to human activities? And these are much more qualitative questions. So we can see the climate's warming through some of the metrics we looked at earlier, global mean temperature, Arctic sea ice, and we can say, okay, the climate is warming, that's unequivocal. With a combination of that data and our modeling tools, we've been able to establish that a large fraction of that warming is due to human activities. In order to address this challenge laid down by the Paris Agreement, we've now set a target of the warming, and that gives us a target for the amount of carbon we can emit into the atmosphere. So this is a numbers game now, and the numbers really matter. And so that's driving a requirement of precision in climate science that I don't think we've had before. And to illustrate that point, this, you can see here, I said there's a straight line between the carbon dioxide emitted and the temperature. The pink here is our level of confidence, or the range of answers that we think are plausible still. And you can see it's very wide. So for the amount of carbon we've emitted into the atmosphere at the moment, we would estimate a warming of between about 0.75 and about 1.5 degrees. Well, that's just too big a range if the target is for 2 degrees of warming or 1.5. So there's a real drive to try and improve our quantitative estimates of these kind of things now, and that's a major challenge for the scientists. Okay, so what about weather and climate extremes in the future? And I'm going to talk about this in relation actually to present-day climate risks. So those of you with memories will remember that winter 13-14 was an absolute stinker, with just depression after depression coming across the Atlantic, and it rained a lot, and we got huge amounts of flooding during that year, particularly in this part of the world, actually. And this precipitated a government review called the National Flood Resilience Review, so trying to understand were the defences appropriate, and was that year unusual? How unusual was it? It broke records, but does that really make it unusual, and can we count on it not happening again? So this is showing the monthly rainfall actually in the southeast of England from 1980 up till that time. And the black line here is showing the observations. So as you know, as a citizen of the United Kingdom, some winters are wet and some winters are not quite as wet as the wet ones. So, you know, it ranges from 25 to 150 millimetres per year in southeast England. And 2014 was this data point here. So you can see it was really substantially higher than the previous record. And so my predecessor, Julius Slingo, was asked repeatedly in the media, is this climate change? Should we expect this in the future, et cetera, et cetera. So what we decided to do was to use our modeling, our simulation tools. So our climate models, these are tools that simulate the oceans and the atmosphere and the weather systems that get generated. Use those to make simulated winters over the UK and see how much rain fell in these simulated winters. And the reason we did that was because in the observations, we know the climate's changing, right? So we don't want to go back too far. So in the observations, we really only use about 30 years. So we've only got 30 examples of winter rainfall. So, you know, maybe this is just what we should have expected, but we hadn't seen it before. So we need a synthetic way of estimating how unusual that was. And we did that using our weather and climate models to make winters that could have happened in the UK but haven't yet happened, so present-day climate, and looked at the rainfall that was in those simulations. So some of these red lines show examples of those simulations, and you can see they bounce up and down, and gosh, look, here's a simulation that looked a bit like that winter. Now, the sharp-minded amongst you are going to say, you're not going to trust these models to tell me how much rainfall it's going to do in the winter. So, of course, behind all this, there was a whole bunch of checking. But one of the, I think, most persuasive tests that we did was for this winter, where actually there's a little bit more rainfall than we saw in 2013-14. We showed some of the charts to one of our chief forecasters and said, well, we showed him some charts from 2014, and we showed some charts from this simulated year. Said, which one's the simulated and which is the real? And he couldn't tell the difference. So it wasn't a bonkers year. It was just a year that had lots of storms, and they kept coming. So putting this together, the observations showed this kind of range. You can see it here. somewhere between 50 and 100 millimetres is kind of normal. The peak was just over 150, but this year was 200. By simulating 1,000 winters that could have happened in the UK with our models, we were able to see just how often we popped above this 200 mark. And it wasn't that unusual, actually. We just had been lucky or unlucky that we hadn't seen it before. So I think I'm going to probably move on. And the punchline from this is that, on average, there's a 10% risk of an unprecedented rainfall in any winter in any one region. So if we divide the UK into these regions, what this model world tells us is there's 1 in 10 chance of breaking a record in a region of the UK. I can talk about what that is, like southeast, southwest, in any winter. So this is actually quite a big chance that we're going to see something that we haven't seen before. And this isn't climate change. This is just because we get wild weather in the UK and it varies a lot. So when you add climate change to that, it's an interesting question. So as I say, this then informed the National Flood Resilience Review. In fact, I think Storm Brian, which we had 2 weeks ago at the beginning of the half-term week, they deployed some of the new storm defences in Foy down in Cornwall because there was a high tide and a storm surge built onto that. And those sort of came out of this kind of work. Okay, I think, let me just mention, so for the experts, what we would have previously done is something called extreme value theory to estimate these based on the observations. What the new technique enables us to do is really tighten the confidence on what might happen. And also it gives us a much deeper view on the weather systems that are bringing the rain. Okay, so something about weather hazards for present day, but you can see in a future climate, you might want to know how those probabilities are changing, and you might want to expand it into heat waves. And actually something we're working on right now is we think of climate change as warming, so we forget about the cold events. And actually, for early deaths, cold events still provide more early deaths in the UK than heat waves because of the kind of climate we live in. So in a changing climate, of course, we will still have cold winters as well as the mild, wet winters. But how many cold winters will we have, and how might that change in the future? So the method I just described, we're working on right now to try and understand that kind of dynamic. Okay, so moving on to the fourth of my questions now, on to the risks of impacts. I have to say this is the quietest audience I've ever spoken to. And what makes it even more surprising is there are some undergraduates in the room. So I've taught in universities for 20 years, and you are a quiet bunch. Okay, so I kind of like this framework. So the question is, what are the risks and opportunities associated with climate change and how we might deal with that? And I suppose what this diagram does to me is it helps me understand the role of the Met Office in this world. So what this diagram is trying to say is that the risk of something, like the risk of a flooding event or the risk of your house being flooded, is a combination of three things. Firstly, there's a hazard. So if you live by the coast, that hazard might be a high tide with a storm surge onto it. The vulnerability might be whether or not you've got some kind of sandbags or flood defense to try and protect your house. And then the exposure is precisely where is your house. So the Met Office is clearly centered in this hazard element of that kind of matrix, if you like. And what we do is work with people, for example, in Exeter University quite a bit on understanding vulnerability and exposure to put that together and make it, for example, into a flood warning. To give you an idea of how we've used that in weather and climate scenarios, we've been thinking quite a bit about the food shocks. So what is the resilience of food production to some of these climate events, and how might that change in the future? So in this particular example, we were thinking of maize production. And there are two regions of the world that produce almost all of the maize. So the US and then the eastern seaboard of China. And so the question is, if a weather event or a season of poor weather for growing maize hits both of these bread baskets at the same time, what's the chance of that? So the way we address that is firstly by thinking about those possible weather events, as I showed for the flooding for the UK. So we looked at the chance of drought in this region over the US and this region over China, and then we looked at the chance of them happening concurrently. We were then able, working with some crop scientists, able to understand the weather variables that tell us whether or not a crop will fail, and there are some fairly well-established relationships that we could use to do that. And then we can estimate the probability of a severe maize production shock in present-day climate due to this water stress. And the results were surprising, I think. The chance of a shock in one of the bread baskets is reasonably well-established, sort of 1 in 10, 1 in 20, something like that. The chance of failures in both baskets, according to this analysis, I wouldn't stake our reputation on the precise numbers, something like 5% chance per decade. So 1 in 20 chance of both bread baskets failing in any 1 year. And again, the question then is begged, okay, that's in present day climate, well, what about in future climates? So you can see the kind of things that we as climate scientists are now trying to do is to understand how those weather and climate hazards combine with agricultural practice or flood defences or drainage systems in cities is a high interest in China, for example, with their massive urbanisation problem, you know, to actually compute these impacts and then build some resilience to them. And as I mentioned at the beginning, particularly in the developing world. Okay, so having skipped a section, I'm now running a little ahead of schedule, but my last topic is slightly different. So what I've tried to give you a flavour of is why my world changed because of the Paris Agreement, and I think your world did too, how that's had an influence on shaping the agenda of climate science, and I've been through some examples there. And I wanted to just end, because I know you have interest at Exeter University on high-performance computing and so on, just to give you a flavour of some of the technology that we use and how that technology is changing and how we will need to harness the new technology to address some of these challenges that I've laid out already. So my tagline here is taming exascale computers, because they're wild beasts. So I'll say a little about these plots, but really this is just background wallpaper. I'm sure many of you are aware that we've seen over the last 30 or 40 years increases in compute power in our computers. And this has been following something called Moore's law, that compute power doubles every few years. And so really, in places like the Met Office and the other major weather and climate centres around the world, we buy a new computer every 5 or 10 years, and that gives us more power that enable us to probe more deeply the questions that I've been outlining. That Moore's law has now stopped, and there are reasons for that to do with the laws of physics and the size of the chips, which I don't really understand too thoroughly, but it just won't continue. So in order to get bigger computers that we will need to really address some of those profound questions I talked about earlier, we will need to use this new type of computer called exascale. And exascale means it will do 10 to the power of 18 calculations per second. Golly, that's a lot. So that we, at the Met Office, we have our new supercomputer we've just had delivered. And this is not an exascale machine, but that does the equivalent of if every person in the world does 1,000 calculations per second, that's how many our machine is doing. So exascale is 3 orders of magnitude bigger than that. So this is really big, even bigger than my iPhone in my pocket. From a technology perspective, the simulation tools we have that we forecast the weather with, and then we use those to do the climate simulations that I've talked about, they simply will not work on these new machines. And there's a raft of reasons for that, but it's partly driven by the requirements of the chips, but it's also where the market for computers is in gaming and phones and stuff means that the chips are being designed with a different architecture. So when you see me and my colleagues looking a bit grey and scared, it's because we're thinking in 5 or 10 years' time, we may not have a machine that we can run our weather forecast on. So this is a major deal for us. Again, for the experts, it's about scalability. So we're used to running the model on 10,000 chips. So our computer has some tens of thousands of compute chips within it. But in these exascale machines, it will have hundreds of thousands of chips. So each chip will do a little bit of calculation for one bit of the world. So this chip might compute the weather over Exeter, and that one might compute the weather over Paris, and so on. The trouble is the atmosphere is a blighter because it communicates at a distance. So these chips have to talk to each other, and that's the bit that kills us, because that's the slow part. So there's a concept called scalability, which means as we add further chips to the computer, are our models able to utilize these additional chips in the right way? And we'd like to follow the red line, and we follow the blue line. So it's a blighter. We've got some work underway to try and address this. But this is a huge challenge to us. And I say this with some feeling in a university, actually, because I think one of the things, we were discussing this earlier, one of the things that we are missing is that this is going to need a new generation of software engineers who know how to operate these new machines, because they are different to the computers we currently have. And so we need a new breed, and I hope Exeter will rise to this challenge and develop some undergraduate and postgraduate courses in this area to try and see us do this. So it's a slightly different one, but it's one that keeps me awake at night, and therefore I thought a problem shared is a problem solved. So, okay, so this is my final slide. So I wanted to just wrap up with a few final thoughts. So just to review what I've said, 2015 was really one of those landmark years, and it was almost exactly 2 years ago. It was December 2015 when the Paris Agreement was signed. So 197 countries all agreeing to this quite rigorous set of emissions targets, the green finance, the loss and damage, that whole thing was laid out there. And I was in the room when it was done, and it was a really kind of inspirational moment, I have to tell you. That agreement, as I think focusing the scientific community's mind on the requirement to actually produce numbers that can help guide and chart our progress towards these challenging targets. So I think a useful metaphor is when you're out to sea and you're trying to bring your boat into harbour, it doesn't really matter if you're 100 metres or half a mile off course, because you're a long way away. But as you come into harbour, your precision needs to increase if you're not going to dent the boat. And I think the same thing's happening here. As we approach 1.5 or 2 degrees, that's our target, and we'll need to get a more and more refined view on where we are and how much carbon we can continue to emit if we're serious about that target. The final thing I wanted to say, which is what's illustrated on this slide, is that the UK is really good at weather and climate science. One of the sponsoring agencies is called the Natural Environment Research Council. So this funds university research in this area. And some at the Met Office, but not too much. We get our funding from other areas. And there was a slightly mischievous previous chief executive of the Natural Environment Research Council who was not a climate scientist. So he thought, I'll get them. We'll do a kind of cost-benefit analysis. How much does their research cost, and how much value does it get? You know, on all these kind of measures, climate science came out higher than, I don't know. I won't name names because I'll insult someone in the room. But the UK is really good at climate science. And I think there are some specific reasons for that. And one of them is that, as I've already said, climate science requires these big tools, these big softwares, infrastructures, big computer programs and a large computer to run those software on. In the UK, we have one climate model pretty much, and that's the Met Office model, and the academic community use that model. So we develop it with elements from Exeter, University of Reading, University of Leeds and Oxford and other places. So it's a true community model that we look after on behalf of the whole community. So that sense of all pulling in the same direction is absolutely vital. Excuse me. The US currently has 5 climate models, and they're all slightly pulling in different directions. So there's not that kind of unity of community that we have in this country. And so one of the motivations, I moved to the Met Office nearly 6 years ago, having spent the rest of my career in universities. And one of the reasons is I think the Met Office is able to provide this kind of central position that helps the university community. So I think that we are making fantastic contributions, the UK climate science community, to these goals. I hope I've given you a sense of the challenge of these goals and some sense of how we're addressing them and some sense of why they're important. And perhaps with that in mind, I'll stop and invite questions. Thank you.
So thank you very much, Stephen.
Pleasure.
Yep, okay. So what's going to happen now is we're going to invite some questions, and as I mentioned before, please wait for the microphone to arrive because we're streaming this on the internet. So who would like to start? One over here.
Hi, thank you very much. Is this working?
Yes.
I've got a question about your very interesting carbon budgeting slide.
Yeah.
My understanding is that as temperatures rise, then carbon sinks, like forests and soils, are going to become less capable of storing carbon and could potentially become carbon emitters. And I wondered, is any of that modelling taking that into account, or is it too much of a kind of unknown right now?
No, that's a great question. And actually, one of the reasons I finished early is I forgot to mention this. So you're the plant, thank you. Only about half of the carbon dioxide that we emit through fossil fuel burning and other things remains in the atmosphere. So the other half, a fraction gets absorbed by plants on land and a fraction gets absorbed by the oceans. And you've got some enormous expertise at Exeter University in both of those areas, as you know. So one of the really difficult challenges for the science related to this is, will plant life continue to absorb at its current rate, or as the climate warms and as the carbon dioxide concentrations go up, will that absorption level off or decline? Because we know that in a warming climate and in a CO2-enriched climate, there are contradictory effects there. So that's a massive challenge, as you know, to this piece of work. And in fact, part of the uncertainty here, or the range of likely outcomes, is associated with that uncertainty. And it's a reminder of, it's a fairly audacious goal, this. What we're trying to simulate and predict here is the fate of carbon dioxide. So we emit it into the atmosphere. Some of it's drawn down to grow plants. Others is drawn down into the ocean to grow plankton, which grow into other things and then sink to the bottom. We're trying to simulate that on computers to chart our future. It's a pretty bold aim and one on which we are making demonstrable progress. So thank you for that question.
Wait for the microphone, wait. It's coming along on your right.
I was just going to say that was my initial question, but there was something I was going to sort of mention because of all the fuss, and I know you don't want to sort of dwell on politics at all, but my understanding is that even though the states have sort of pulled out of the Paris Agreement, they can't actually do so until 2019, and it's very hazy as to whether they'll actually do it.
Yeah.
Because I think that most of the companies in America are moving away and are looking to the future, which will be low emissions.
Yeah.
But I was going to come back to this question of at what point do you sort of set up an equilibrium between the sort of carbon dioxide production and the ability to produce sinks? And that's a really complex question.
Okay, 2 for 1 there. So you're asking about the US withdrawal. So one of the interesting aspects of the US is that the responsibilities for carbon emissions is quite devolved to state and city level. And actually there's very strong evidence that at city and state level there's very strong action to reduce emissions. You need 197 countries to sign up for the agreement. We've got that agreement. If one of the countries isn't responding as it should, then it's for that country really to decide its own fate, of course. You know, we have no control over what the US should do, nor should we. But I think there is evidence that there's a sense that it's redoubled efforts in Europe, particularly, in China. So the kind of the discussion by the US seems to have provided more motivation for other countries. So there's clearly a complex dynamic here. You asked about where we equilibrate in the carbon dioxide. There's one thing to remember here. If we want the climate to stabilize, we need to get to zero emissions, zero net emissions. So a likely way of achieving that is that we will continue to emit some through some kind of fossil fuel burning or something like that. It's unlikely we can get to zero emissions. But for every ton we emit, we'll need to draw down a ton through some means. So there are lots of ideas for how to do this. So one is this so-called carbon capture and storage. I think you know about these things, but I'll say it for the benefit of the rest of the audience. So this is a way of taking the carbon dioxide out of the atmosphere and storing it underground, probably in a liquid form, possibly in the now empty oil wells, for example, that sit under the North Sea. So you take the carbon dioxide out of the atmosphere, it doesn't have its warming effect. So, but the one thing zero net emissions is the thing we need to attain if we want to stabilise the climate. That isn't complicated, and that's what we need to do.
Thank you.
Thank you for the talk. It is really interesting, especially for students, because we're hoping to change this in the future. So a question that really concerns me is, once we get to that 2 degrees threshold, is there actually anything we can do to regenerate resources to actually lower it at any point? It may be obvious to the rest of the room, but it is a question that young people are wondering, what can we do to perhaps reduce it?
Okay, that's a very good question. So you have several questions implicitly there, I think. So the first question might be, why was 2 degrees chosen? The answer to that, it was a judgment. In the range of warming that we're likely to see, certainly over the next 30, 40, 50 years, there probably aren't huge thresholds in the climate system, although you have expertise in the university who are thinking very hard about what those thresholds might be and when they might occur. So it was a judgment, the 2 degrees and the 1.5 degrees, first thing to say. I think the second part of your question is, if we overshoot, can we come back down again? And the answer to that is yes, we can. So actually we've got some really interesting work we're just finalising at the Met Office thinking about this. So it's kind of a cost-benefit analysis you might do here, because if you overshoot, you've got to really aggressively take carbon dioxide out of the atmosphere using these carbon capture and storage or other techniques to bring the climate back down. Remember that plot. The total carbon in the atmosphere is the temperature. So if you want to bring the temperature down, you've got to take stuff out. And that's expensive. So on some metric, and it doesn't have to be financial, on some metric you need to think about the cost-benefit of doing that. And this has been thought about particularly in relation to the 1.5 degrees, because that's a really quite a challenging target. It is possible to do it. I shouldn't say it like that. It's feasible, although whether it's economically possible is an open question and frankly beyond my expertise. The benefits are more complicated because sea level rise has a much slower response. So the lag in sea level may come much later, so it may not save you for if sea level rise is your main metric of change. If you're interested in rainfall, rainfall doesn't go exactly with temperature, so there are a raft of other things that make you wonder whether it really is a good idea or not. Another route, sorry, this is turning into another lecture. Another thing you might do is, rather than overshoot, how about if you deployed some geoengineering to just take the top off? So a temporary geoengineering thing. And again, you could do a cost-benefit analysis of that. It is, in principle, possible to do that, but whether the cost, in some generalized sense, justifies the means is not clear. Yeah.
One over here.
All right. Yes, I'd just like to ask, because you didn't actually mention, there is a budget, as you say, for the amount of fossil fuels we can burn to have a reasonable chance of achieving any particular temperature. And those budgets are really running out quite fast, aren't they?
Yeah.
And I don't think many people understand that. I mean, I believe 2 degrees is the budget for fossil fuels could run out as quickly as 2037 if we continue with our current emission rates.
Yeah.
So that's an issue, isn't it?
Yes, it is. And thank you for pulling me up on this. I fluffed my figures on this, so I've failed my oral exam, I think. The precise number, of course, about when we run out is difficult to pin down because there is that range. But at current emissions, we're talking 20-odd years. Yeah, it's not long at all. So the kind of scenarios that keep us below, or give us a good chance of staying under 2 degrees of warming, imply a peak in emissions between 2020 and 2025. And the reason for that is that we, based on economic modelling and the kind of thinking about how technology could evolve or has evolved in the future, gives us a rate at which we can decarbonise, or an estimate of how quickly that would happen. So that's where these estimates come from. But you're right, it's a big deal for right now. I should say that the UK has a very aggressive policy on this. So in the UK, we have a very sophisticated machinery, political machinery, around the Climate Change Act. So there is a Climate Change Committee which sets a budget. Climate Change Committee is independent of government in the UK. It sets a budget for carbon emissions in the UK, which will help us meet our obligation to these deals. And Parliament is called to account against those budgets. So as I say, the UK has been a good citizen in this respect, I think.
Can I just add one more point?
Yes, please.
Because there's an emphasis, or there's a danger, I think, of relying on geoengineering, because that involves enormous risks.
Yep.
That may get more. If we can't agree to cut emissions, we find it much more difficult to agree on geoengineering when we don't know what climate fallout might come from that.
Yeah, I agree.
And the sheer scale of it that is required, because I seem to remember, I think it was a chap called Václav Smil did an estimate some years ago, in which he reckoned that you'd have to remove 10% of the carbon that we're putting into the atmosphere each year. Would require an engineering installation that might take a generation to install.
Yeah.
You know, it's such a vast concept.
Yeah, that's right. And the ethical and legal implications are unclear. But even the physical implications. So it's unfortunate that this focuses on the global mean temperature. Perhaps that's something I didn't draw out quite as much as I could have done. The regional changes are not uniform across the globe. And geoengineering, while it may keep the global temperature down, its regional expression is much more open. In fact, my distinguished colleague on the left, I think, has thought a little bit about this. So, yeah, geoengineering is a complex subject in itself. Yeah.
Okay, I think I'm afraid going to draw things to a close because we haven't even given Paul Stephen any dinner yet.
Just lemsip.
Just lemps it. But I'm going to invite our Deputy Vice-Chancellor, Mark Goodwin, to come up and give a vote of thanks.
So I'll stand here because I don't have a microphone clipped on, but a very good evening to you all. As Deputy Vice-Chancellor for External Engagement here at the University. It's my real privilege to have been asked to propose a vote of thanks, especially given the speaker tonight. So firstly, can I really thank Stephen for delivering such a fascinating lecture. A fascinating lecture which ranged very broadly on this hugely important topic. And I think it's a topic which is of great interest to us all in the audience. And I think that was evident from the questions, but also evident from the questions, it's a topic of great concern to us all. And I think it's really vital for us to know that this work is going on in Stephen's team under his leadership at the Met Office. As Stephen said at the beginning, the partnership between the university and the Met Office is very strong, and it's actually allowing world-leading researchers here at the university and at the Met Office to really focus on climate science and to uncover some of the data that Stephen used in his talk. Indeed, I think the university and the Met Office have now collaborated on more than 120 projects focusing on climate science in one way or another. So that's testimony to the partnership. And we were delighted that Stephen very kindly accepted our award of an honorary professorship here to go alongside his substantive professorship from the University of Reading. So thank you, Stephen, for the honour of accepting that for us. Stephen so ably described the impacts of climate change. They are, as he said, evident both here and across the globe. We heard him talk about changes in temperature, changes in extreme weather, diminishing snow and ice, rising sea levels. And I think through the kind of robust, impartial and targeted science that he talked about, we can now begin to really understand these changes and to really begin to understand their potential effects. And above all, we can begin to work together, as Stephen pointed out, on mitigating and managing some of the risks of climate change for future generations. And one of the questions was about what we can do as future generations on this. Stephen also talked in detail about the historic Paris Agreement, which marked a turning point in climate negotiations and what we all have to do next as a result of that agreement. The university is committed to doing its part in that. We're delighted to be attending the upcoming UN Conference of Parties for the first time ever as an official observer, and we'll be doing that alongside our friends at the Met Office, and very few universities worldwide have that status. And one of the reasons why we were given that status came from the work of one of our recent European-funded projects on high-end climate impacts and extremes. And that project considered the possible impacts of global warming at 2, 4, and 6 degrees. And one of the questions was about the threshold and where we got the threshold from. And we're already doing work to look at what might happen if we don't make the 2 degrees. What happens if it's 4? What happens, God forbid, if it's 6? So we're beginning to do that research already here. And again, it's not by chance that that project was led by Professor Richard Betts, who holds a joint appointment at both the university and the Met Office, and we were delighted to be able to contribute that. And again, it shows the importance of the two institutions working together and the importance of evenings like this where we can draw on Stephen's expertise to give a public lecture. It's absolutely fantastic. Just before I close, I wanted to draw your attention to 2 upcoming lectures which you may be interested in if you've attended this one. If you want to go to the university's Eventbrite page, you can find out more. The first one is taking place on the 8th of November, so a week tomorrow. It's by Niall Stanage, who's a White House correspondent, and he's talking 1 year to the day since Donald Trump won the presidency, and he's talking on where we are now, how we got here, and what happens next, which in the wonderful world of Trump, I guess, is a kind of constantly moving challenge. But of course, the US government's actions around the Paris Agreement, and again, we had a question on that, are not without significance. So if you're interested in this topic, that promises to be a fascinating lecture, although I guess the events of yesterday may well crop up in that lecture at some point. And secondly, a team of Met Office scientists will be delivering a family-friendly Christmas lecture on the 13th of December, in which they are uncovering the secrets of meteorology. and that promises to be fascinating, and that's designed for families and for children to come along and hear from the scientists at the Met Office on those secrets. And that's on the 13th of December. So if you want to put that in your diary as well and have a look at the Eventbrite page, more details on that will be published shortly. But again, it's great to have teams of staff from the Met Office coming over here to give these public lectures. So can I finally thank you all for attending, especially given Bake Off. I didn't realise it was the Bake Off final tonight, but I'm even more impressed that so many of you have turned up. I did realise it was the Champions League tonight, which tells you what I watch on my telly. So again, if you've got the competing attractions of Bake Off and the Champions League, it's fantastic that you've all come out tonight to hear this. So a huge thank you to you all. And finally, a massive thank you for Stephen for providing such a fascinating insight into the world of climate science after the Paris Agreement. Can I ask you to express your thanks in the usual way?